So our next speaker will be Aggelos Biboudis, who is going to be talking about stream fusion to completeness. So figuring out how to take high-level stream-based computations and generate optimized implementations that are similar in performance to handwritten code. Everyone in session has tested their computers against the projector. Good.
So, thank you for the introduction. Hello, everyone. My name is Aggelos Biboudis. I am from the University of Athens. I'm finishing my PhD in a month, I think. And this is a joint work with Oleg from Tokyo University, Palladinos from National Information Technologies, a company in Greece, and my advisor, Yannis Smaragdakis, from the same university, University of Athens. I'm going to talk about our paper, Stream Fusion to Completeness. So, we have designed a library, we propose a library design for very, very fast streams. Streams mean an overload term, and means different things to a lot of different people. For us, streams are libraries, algorithms, that process a stream of elements functionally with all the well-known functional combinators from that make functional programming matter, essentially. And map, filter, folding, fold patterns, unfolding, zip with combinators, and all that make pipelines essentially understandable and easy to declare. That kind of streams do not store any elements during the pipeline processing. They are lazy by default. They can handle both finite or infinite streams, and they are one-shot. And for our kind of streams, we support bulk data processing. So high performance, really, really high performance for bulk data processing. And this is a terminology and a goal that we have adopted from the Java 8 streams, but we do it really, really fast. So we can have up to 50x times faster code than mainstream libraries out there, like Java 8 streams or other collection APIs. And the second point is that we support a wide range of combinators to be employed, and we also accommodate complex combinations of those. And essentially, we have implemented a scheme of stream fusion in the broader sense of the term by generating loop-based fused code with no allocations. And we did that by adopting multi-stage programming as the main style for us for our implementations. And in this example, we see a very simple pipeline. Ignore the weird brackets and the tilde operator there. And essentially, we implement a sum of squares operation. So there are three combinators used: of array, that creates streams from an array, from data that maybe fit into memory. This array is piped to a map combinator, and element-wise a lambda function is applied that squares its element, and in the end everything is folded together with a summation function. So our library is going to generate super fast code, and the code that is going to be executed by the machine is this one, that contains mutation, contains the array declaration there explicitly, a very quick language construct provided by Camel, which is 4 in that particular case, known bounds, everything is fused together, and the result is returned to the users. So we take a first hint of what we may have implemented. have implemented a library that is going to generate super fast code. We didn't rely on hacking the compiler, on optimizing the optimizer, or making any knowledge, domain-specific knowledge available to the compilation process, for example, rewriting an AST, an internal data structure there, or anything else. We have put all our effort into the library to generate that kind of code. And this is going to be our main example through the rest of the talk. But we can handle much more complex cases. I'm not going into details with this one, but we can generate really fast code for a zip with combination, a combinator when passed with an infinite stream and a finite one. The upper stream is the finite one, is short-circuited with a tape combinator. You see there that we take the 12 first elements. The other one is an infinite one, which is also flat-mapped with another infinite one, and is also circuited. Anyway, this example is much more complex, and we don't rely on a general-purpose compiler to produce fast code for that. So we guarantee performance. We have no intermediate results. No, we do not rely on storage allocation on internal buffers. We do not create any closures. No things are generated in the final code that is going to be executed. And also, function calls are not there. Everything is inlined explicitly by us for the pipeline processing. And every internal data structure that we have used to compute a very fast piece of code are not reflected to the generated code. Everything happens at, let's say, compile time. So no deconstructions or constructions of tuples or other data structures that carry information around at runtime. And we have implemented this library design into two libraries. The first one is in OCaml, by using bare metal OCaml as the front end that gives us the opportunity to multi-stage program this library. And the other one is for Scala implementation using Scala LMS. And that gave us a really nice environment to evaluate, to assess the performance on the JVM. So let's see some benchmarks first and then go through the rest of the talk. In this first slide, we see the OCaml benchmarks. The lower is the better because the vertical axis is average millisecond per operation. On the horizontal axis, we see our benchmarks. We make benchmarks gradually more complex. The first one is sum. For example, the second one, sum of squares. We employ a filter combinator on the third. Cartesian product demonstrates nested loop fusion. Zip width is there, multiple filters, maps, and then reification of loops with much more complex combinations of zip and flat map. Our library performed with the green bars. They are the ones that are squeezed together with between the other ones. Loop-based handwritten code is with blue, and these are target measures. These are the target numbers that we want to achieve. The code is equivalent, of course. And just for a position of how well we did in terms of a mainstream library, for example, using batteries, we compare the results here. And some bars are truncated. So anyway, the other setting that we have is through our Scala implementation. Scala provides a multi-stage programming framework as well with Scala lightweight modular staging. But playing around with the JVM made us happy because we could create some pipelines using Java 8 streams. The Java Stream API was introduced by Java 8, I think 2 years ago, and they have a really fast implementation. So, the design decisions that are put into the Java 8 stream library combined with the sufficiently smart, actually super smart JIT compiler of the JVM, made the sum and sum squares benchmarks to be full fused. The Java 8 code is with yellow, and our code is again with green. But things are starting to go a little bit off with sum of squares even, and even worse with nested loop fusion that was not demonstrated at the Cartesian product, and there are some other results as you see over there. The interesting part, if you notice that, is that there are no bars for the benchmarks that have a zip combinator. Why is that? Because the Java 8 Stream API does not provide a zip combinator, because, and that was by design, because it wasn't easy due to the library decisions that the authors have made to implement it in a very efficient way. So yes, again we have baseline 100 loops with bluish colors. Scala and Java in 100 forms are depicted with blue lines over there, and again our implementation has to compete with the baseline and not mainstream libraries. Yeah, so a very quick recap of what is multi-stage programming. Multi-stage programming is, let's say, a style and think of handling explicitly code templates as first-class values throughout your program. So essentially, you don't have only compile time and runtime execution, but you have stages in between them. So in order to defer the evaluation of an expression from compile time and explicitly hold a reference to it at runtime, you can put these brackets over there and essentially defer the execution. And these patterns, these code templates can have holes in them. And then you can splice other templates in them. And this can be done by synthesizing code, essentially by function composition. So CF of C, which is a function application of the CF function to the C value up there, is going to produce something like that. Over the next few minutes, I'm going to talk about our thought process of how we designed our libraries. And there are three main steps that we took. But let's start from somewhere. Let's start from a type signature that's going to represent our streams. We adopt an F-algebraic way to express our streams. For those of you, all of you who are familiar with functional programming, we rely on an unfold. For those of you who are familiar with maybe iterators in Java and object-oriented programming, this is essentially iterator pattern. And we take the type signature, that can ignore the code ties for a moment, that has a hidden state, that is a pair of a hidden state, a stepper function, and the stepper function, when applied to hidden state, is going to produce another shape of our stream. And the stream shape for us is essentially a list functor. And now it's a little me time as the developer of a multi-stage program. I can do binding time analysis on my own and say which parts of the program are going to be considered static, and they are going to be partially evaluated in the finally generated code, and which parts can be considered as dynamic. And in this code, we don't know anything about the internal state over there, so this can be considered dynamic, and it pollutes the whole type signature. And this is the first step that one can do. So map implementation of by using this pattern can be this one, and the stepper function of the inner stream of the newly returned stream is going to return a code template that does pattern matching over the return value of step applied to the stream. And we can do some case analysis by consulting our stream functor, and we can have the nil case and cons case, and then we return a cons with the mapping function that we took as parameter. And then everything is packed together with a tuple, the new state, and new step. So yes, so the first result would be this thing. No intermediate allocation, because we get that for free from the original design that we have picked. Function inlining, yeah, we did that by using multi-stage programming and guiding inlining of function method bodies. But we have some various overhead. So if you notice, we off-array, which could have a similar implementation, could contribute this template of code, map contributes this one, this one. So at runtime, we have to execute this code that is going to perform a deep pattern matching, nested pattern matching case. So you have to do something about that. What is known at this, what we can contribute as domain experts to this design, we can contribute the structure of the stepper. And we can employ continuation passing style to improve binding time analysis through our library. And essentially, here, as you see, stream shape is static and can be factored out of the dynamic code. So the new type signature of new step take a continuation, and we apply to the continuation the nil case and the cons case. And we have reached that kind of result, that the stepper is inlined, producers and consumers are brought together. So if then let binding of the element, and then the multiplication, and then elements of the fold operations are here, everything is fused, but we didn't do anything about pattern matching over the hidden state. So, okay, let's go to eliminate that as well. We can fuse the state and essentially eliminate the allocation of the pair, because the state for our streams is the index and the array itself. And the implementation of array, this combinator can be that one that initializes the state by performing a let binding here and making the rest of the program know about the structure of the state. And the stepper function that knows the current form of the state. So we can interpret this into two ways. The first one is that we transform a code template of a tuple of an integer and an array to a tuple of two code templates. So again, we reified into our library the structure of our state, which is a tuple in that case. Let's see what that generates. It generates a code without any pattern matching, but there is still something that we can do to make that better. You see here the tail recursive loop, which can be fine in this case, but if we want to port that design to the JVM, that cannot be done efficiently. So, and the other reason, there are two reasons. The other reason is that if we want to refile loops together, consider the zip combinators or nested loops with zip and all that, we cannot explicitly fuse the iterations in that form. So we have to deconstruct the iteration and go from a tail recursive loop to a for-based one or a while-based one. And the final step, for the sake of the talk, because there are some more steps in the paper, we can generate imperative loops by further deconstructing our producer. So for that particular example, we have packaged together everything in a for data constructor, because we start from a for-based loop. And the for-based loop knows how to return the code template that calculates the upper bound, initialization, and indexing functions again. Later, we may need to transform for into while for various reasons. So we can do that. And the result from that piece of that step of our thought process can be something like that. So this piece of code is loop-based and it is completely fused. As you see here, for that simple example that I have shown you earlier, we didn't need to transform the for-based iteration into a while. So it can stay for here, because for is a very fast loop form for a call. And remember how we started with the structure of unfold, which was a pair of a hidden state and a stepper function. And that is the final data type that can handle much more complex cases, but way too many. For example, we know we have baked-in knowledge, domain-specific knowledge about linearity. Filter breaks linearity because it can return 0 or 1 elements. Flat map breaks linearity because it can return 0, 1, or many more elements. Sum ranging and infinite streams, that is also a piece of domain-specific knowledge. So short-circuiting and unfold, think about generating more tests to be hoisted into a while loop, and then fusing parallel streams. So we have started from somewhere, and this is the final data type, the piece of domain-specific knowledge that we expected a general-purpose compiler to be able to handle anyway. So the takeaways for us is that we handled stream fusion as a domain-specific problem, optimization. And domain-specific optimizations, our thesis is that are better tackled outside the general-purpose compiler, maybe by using multi-stage programming. And we are fan of multi-stage programming, as you have may guessed. And that keep in mind that if you want to use multi-stage programming, start with that in mind. It isn't a simple sprinkling of code annotations over a legacy code just to create a very fast, partially evaluated structure of code. And these two libraries are under this URL. Simonas is the name of our project, which is a very cool hydronym that resembles to streams, hydronym of a Greek river. And you can read a lot more about the design in the paper. Thank you very much.
Okay, we have time for a quick question or two while the next speaker sets up. Don't be shy. Raise your hand.
So this was quite impressive, but do you have any guarantees?
Guarantees that?
That you will get rid of everything?
Yes, because effectively our code does not introduce anything. So if you inspect the code of our library, this is going to reflect what is going to be generated. And in our code, there are no func pairs, etc. All are static things that are going to be generated. They are going to, every intermediate data structure is going to be used by us to drive this computation of the final code. So it's not going to reflect it on the generated code. Thanks.
Hello. Hi. It's impressive. So what's the catch?
Yeah. Sorry. So the catch. Maybe somebody is going to be scared by the staging annotations in OCaml. Okay, that's understandable. But you have the Scala LMS and create a library that partially evaluates stuff there, and there are no staging annotations. And everything is derived by types. But in the OCaml case, using MetaCaml, you may find handier that you have staging annotations. So there is a bit of decision for someone who wants to create such a library or to use this library in his code. And essentially, the design that we are based on is based on the Java 8 streams philosophy. So no storage allocations, and streams are one shot. So if you want to use these for dataflow programming, branching, or reusability of existing pipelines, this may not be the most efficient library. Our library is about bulk data processing. So you have everything in memory, and then you can operate over that data structure really, really fast.
Okay, thank you. Let's take further questions offline.